Hey guys, tonight we're talking about something that's happening right above your head, right now, as you listen to this. Thousands of pieces of metal, plastic, and debris are screaming through space at 17,500 miles per hour. They're invisible, they're silent, and they're growing more dangerous every single day. This is the story of space debris and why it might be the most terrifying threat you've never thought about. So before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And let me know in the comments where you're tuning in from and what time it is for you. It's always fascinating to see who's joining us from around the world. Now, dim the lights. Maybe turn on a fan for that soft background hum. And let's ease into tonight's journey together. Right now, as you're sitting there are over 34,000 pieces of trackable space debris larger than 10 centimeters orbiting Earth. But that's just what we can see and track. The real number, including all the fragments smaller than 10 centimeters, is estimated to be over 130 million pieces. 130 million. That's like having every person in Mexico turned into a high-speed projectile circling our planet. But here's where it gets truly terrifying. These aren't just floating peacefully like leaves on a pond. They're moving at speeds that would make a Formula One car look like it's standing still. The average piece of space debris in low Earth orbit travels at approximately 17,500 miles per hour. To put that in perspective, a bullet from a high-powered rifle travels at about 2,700 miles per hour. Space debris moves more than 6 times faster than that. What does that mean in practical terms? It means that a piece of debris the size of a marble has the kinetic energy of a hand grenade. A fragment the size of a paint chip can punch through the hull of a spacecraft like it's made of paper. And a piece the size of a softball could completely destroy a satellite worth hundreds of millions of dollars. Or worse, kill every person aboard the International Space Station. This isn't science fiction. This isn't a distant future problem. This is happening now, today, and it's getting worse exponentially. The story of space debris begins, ironically, with one of humanity's greatest achievements. On October 4th, 1957, the Soviet Union launched Sputnik 1, the first artificial satellite. It was a simple aluminum sphere about the size of a beach ball, weighing just over 180 pounds. For 96 days, it orbited Earth, beeping its radio signal and announcing to the world that the space age had begun. But when Sputnik's batteries died and it finally fell back to Earth in January 1958, it left something behind. Not just the satellite itself, but the rocket stage that had carried it into orbit. That spent rocket stage became Earth's first piece of space junk. At the time, nobody thought much about it. Space was infinite, after all. What was one piece of metal floating around up there? That attitude would prove to be catastrophically short-sighted. As the space race intensified between the United States and Soviet Union, launches became more frequent and more complex. Multi-stage rockets shed their components as they climbed toward orbit. Satellites were deployed from protective shrouds that were then discarded. Mission after mission added more and more debris to the growing cloud of artificial objects surrounding our planet. In the early days, space agencies operated under what could charitably be called a big sky theory. Space was so vast, they reasoned, that the chances of two objects colliding were infinitesimally small. They couldn't have been more wrong. The first major wake-up call came on September 15, 1961, when the Soviet Union conducted an anti-satellite test. They detonated a nuclear device in space, creating an electromagnetic pulse that disabled several satellites and created thousands of new debris fragments. But even that wasn't enough to change attitudes. The Cold War was raging, and both superpowers were more concerned with beating each other to the moon than with keeping space clean. Throughout the 1960s and 70s, the debris population grew steadily but relatively slowly. Most satellites were large, expensive, and built to last. When they failed, they typically failed intact, becoming single large objects rather than clouds of fragments. The real explosion in space debris was still to come. The 1980s marked a turning point. Commercial satellite launches became more common. Military space programs expanded, and most significantly, satellites became smaller, cheaper, and more numerous. The attitude shifted from launching a few expensive, multi-purpose satellites to launching many smaller, specialized ones. Each launch meant more potential debris, but it was what happened in the 1990s and 2000s that truly opened the floodgates. The commercialization of space accelerated dramatically. Companies like Iridium launched constellation after constellation of satellites. Some succeeded, others failed spectacularly, but all of them added to the growing debris field. The turning point that made space debris a crisis rather than just a problem came on January 11, 2007. On that day, China conducted an anti-satellite test, deliberately destroying one of their own weather satellites, Fengyun 1C, with a kinetic kill vehicle. The satellite was struck at an altitude of 537 miles above Earth. The impact was devastating. The collision created over 3,000 trackable pieces of debris larger than 10 centimeters, and an estimated 150,000 pieces larger than 1 centimeter. Overnight, China had increased the total amount of trackable space debris by about 25%. These fragments, traveling in highly elliptical orbits, continue to pose a threat to spacecraft today. More than 15 years later, the international space community was outraged. Unlike the nuclear tests of the 1960s, this was a deliberate creation of debris in the modern era, when the dangers were well understood. It was seen as an act of environmental vandalism on a cosmic scale. But the damage was done, and the debris will remain dangerous for decades to come. 2 years later, the situation got even worse. On February 10, 2009, 2 satellites collided directly over Siberia. The active Iridium 33 communication satellite, owned by the United States, smashed into the defunct Russian military satellite Cosmos 225, one at a combined speed of over 26,000 miles per hour. The collision was particularly significant because it was the first time 2 intact satellites had collided accidentally. It created over 2,000 new pieces of trackable debris and countless smaller fragments. The impact was so violent that pieces of the satellites were scattered across hundreds of miles of orbital space. What made this collision especially troubling was that it was entirely predictable and entirely preventable. Both satellites were being tracked by ground-based radar systems. Space surveillance networks knew their orbits and could have predicted the collision days in advance. But there was no formal system in place for satellite collision avoidance. The operators of Iridium 33 were never warned that their satellite was on a collision course. This collision finally forced the space community to take debris seriously. Collision avoidance became a standard part of satellite operations. The U.S. Space Force now routinely issues collision warnings to satellite operators when their spacecraft are predicted to come dangerously close to debris or other satellites. But by then, it was almost too late. The debris population had reached a critical threshold. To understand why space debris is so dangerous, you need to understand orbital mechanics and the physics of high-speed impacts. When we talk about objects in space moving at 17,500 miles per hour, it's easy for those numbers to become abstract. Let's make them concrete. Imagine you're driving down the highway at 70 miles per hour. That's fast enough that a collision with another car could easily be fatal. Now imagine you're going 250 times faster than that. That's the speed of space debris in low Earth orbit. At those speeds, the physics of collisions changes completely. When two objects collide at orbital velocities, it's not like a car crash or even like being hit by a bullet. It's more like a controlled nuclear explosion. The kinetic energy of a moving object is calculated using the formula 1/2 mass times velocity squared. That squared term is crucial. It means that if you double the speed of an object, you quadruple its kinetic energy. If you multiply the speed by 10, you multiply the kinetic energy by 100. This is why a paint chip in space can be lethal. A paint chip weighing just 1 gram, traveling at typical orbital velocity, carries more kinetic energy than a 1-pound object moving at 100 miles per hour. When that paint chip hits a spacecraft, it doesn't just chip the paint. It punches through metal like a tiny missile. NASA has conducted extensive testing to understand these hypervelocity impacts. They've fired projectiles at spacecraft materials using light gas guns that can accelerate small objects to speeds approaching orbital velocity. The results are sobering. A piece of debris just half an inch in diameter, weighing less than an ounce, can punch completely through the hull of a spacecraft and create a hole several inches wide on the exit side. The impact creates a shower of molten metal and vaporized material that can damage equipment far from the impact site. Larger pieces of debris don't just punch holes, they obliterate whatever they hit. A piece of debris the size of a marble carries enough energy to destroy a small satellite entirely. A piece the size of a softball could catastrophically damage even a large spacecraft like the International Space Station. But it's not just the immediate impact that's dangerous. When debris strikes a spacecraft, it doesn't just create a hole and bounce off. The impact creates secondary debris. Fragments of both the projectile and the target are scattered in all directions, each becoming a new piece of debris traveling at orbital velocities. This is how a single collision can create thousands of new debris fragments, each potentially dangerous to other spacecraft. It's a chain reaction that's already begun and is accelerating with each passing year. The physics gets even more complex when you consider the different types of orbits. Satellites in low Earth orbit, between 160 and 1,200 miles above Earth, travel at about 17,500 miles per hour. But they're not all going in the same direction. Some satellites orbit from west to east, following Earth's rotation. Others orbit from pole to pole. Some follow highly elliptical paths that take them from very low altitudes to very high ones. When satellites in different orbits collide, their relative velocities can be much higher than 17,500 miles per hour. The worst-case scenario is a head-on collision between two objects in polar orbits, one going north and the other going south. In that case, the relative velocity of impact can exceed 35,000 miles per hour. At those speeds, Even tiny pieces of debris carry enormous destructive power. This is why space agencies track debris so carefully. Every piece of debris larger than about 4 inches is catalogued and monitored. Its orbit is calculated and predicted days or weeks into the future. When a piece of debris is predicted to come close to an active satellite or the International Space Station, operators can move their spacecraft out of the way. But tracking and avoiding debris is becoming increasingly difficult as the debris population grows. Each new piece of debris means more potential collisions to calculate and avoid. And with over 34,000 trackable objects already in orbit, the computational burden is enormous. Worse, the 4-inch threshold for tracking is a limitation of current radar technology, not a measure of safety. Pieces of debris smaller than 4 inches can still be deadly, but they're too small and too numerous to track individually. Spacecraft operating in areas of dense debris essentially have to fly blind, hoping that the statistical probability of collision remains low. But as the debris population grows, those statistics are becoming less and less comforting. The most frightening aspect of the space debris crisis isn't what has already happened. It's what could happen next. Scientists have identified a scenario so catastrophic that it could effectively end humanity's ability to explore space for generations. It's called the Kessler Syndrome, named after NASA scientist Donald Kessler, who first described it in 1978. The Kessler Syndrome describes a cascade of collisions that becomes self-sustaining. Here's how it works. As the debris population in orbit increases, collisions become more likely. When collisions occur, they create more debris, which makes further collisions even more likely. Eventually, you reach a point where the rate of new debris creation exceeds the rate at which debris naturally falls back to Earth and burns up in the atmosphere. Once that tipping point is reached, the debris population begins to grow exponentially. Each collision creates hundreds or thousands of new pieces, each of which can cause more collisions. The cascade accelerates until entire orbital regions become unusable. In the worst-case scenario, low Earth orbit becomes so densely packed with debris that it's impossible to launch spacecraft without them being destroyed almost immediately. Earth becomes surrounded by a shell of high-speed projectiles, effectively trapping humanity on the planet's surface. This isn't science fiction. It's a scientifically recognized possibility that keeps space policy experts awake at night. Some scientists believe we may have already passed the tipping point in some orbital regions. The evidence is troubling. The debris population in low Earth orbit has been growing steadily for decades, despite natural atmospheric drag that should cause debris to fall back to Earth. The growth rate has accelerated in recent years, particularly after the Chinese anti-satellite test and the Iridium Cosmos collision. Computer models of the future debris environment paint an alarming picture. Even if we stopped launching satellites entirely today, the existing debris population would continue to grow through cascading collisions for the next 200 years. If we continue launching at current rates, some models predict that low Earth orbit could become essentially unusable within 50 years. The economic implications are staggering. The satellite industry is worth hundreds of billions of dollars. Satellites provide services that we take for granted: GPS navigation, weather forecasting, television broadcasting, internet connectivity, and military communications. If the Kessler Syndrome makes satellite operations impossible, It would represent one of the greatest economic disasters in human history. But the implications go beyond economics. Earth observation satellites monitor climate change, natural disasters, and environmental degradation. They provide early warning of hurricanes, track deforestation, and monitor the health of crops. Losing these capabilities would blind us to changes in our own planet's environment. Scientific research would suffer enormously. Space-based telescopes, like the Hubble Space Telescope and the James Webb Space Telescope, have revolutionized our understanding of the universe. If the Kessler syndrome prevented us from launching new telescopes or maintaining existing ones, astronomical research would be set back by decades. Human spaceflight would become impossible. The International Space Station operates in low Earth orbit, the region most at risk from the Kessler syndrome. If debris density reaches critical levels, the station would have to be abandoned. Plans for commercial space stations, lunar bases, and Mars missions would all have to be shelved indefinitely. Perhaps most frightening of all, the Kessler syndrome could be triggered by a relatively small number of additional collisions. Computer models suggest that as few as 5 or 10 major collisions in the right orbital regions could push the debris population past the tipping point. This means that a single reckless act, like another anti-satellite test, could trigger a cascade that would lock humanity out of space for generations. It's a sword of Damocles hanging over our heads, held by increasingly fraying thread. The threat is so serious that it's reshaping space policy around the world. International guidelines now require satellite operators to plan for the disposal of their satellites at the end of their missions. New satellites must be designed to either fall back to Earth within 25 years of the end of their mission, or be moved to a graveyard orbit where they won't interfere with active satellites. But these measures, while important, may be too little, too late. They don't address the billions of pieces of debris already in orbit, and they don't prevent the next major collision that could trigger the cascade. Some experts argue that we need to move beyond prevention to active cleanup. Several companies and space agencies are developing technologies to capture and deorbit space debris. These range from giant nets and harpoons to laser systems that can alter the orbits of debris pieces and cause them to fall back to Earth. But active debris removal faces enormous technical and legal challenges. The debris pieces are small, fast-moving, and unpredictably shaped. They're also distributed across thousands of miles of orbital space. Cleaning up even a small fraction of the existing debris would require hundreds of missions and cost tens of billions of dollars. There are also legal complications. Much of the debris in orbit technically belongs to the countries that launched the original satellites. International law requires permission before removing another country's property from orbit, even if that property is a piece of dangerous debris threatening everyone else's satellites. Despite these challenges, the urgency of the problem is driving innovation. Japan's space agency has tested an electrodynamic tether system that can drag debris out of orbit using magnetic fields. The European Space Agency is developing a mission called Clear Space One that will use a robotic arm to capture a piece of debris and drag it back into Earth's atmosphere. Private companies are also getting involved. Several startups are developing debris removal technologies, hoping to create a profitable business out of cleaning up space. The challenge is making the economics work when the customers, satellite operators, don't directly pay for the damage that debris causes to the space environment. But even if active debris removal becomes technically and economically feasible, it faces a fundamental problem of scale. New debris is being created faster than any conceivable cleanup system could remove it. Unless we dramatically reduce the rate at which new debris is created, cleanup efforts will be fighting a losing battle. This is why many experts believe that preventing the Kessler syndrome will require more than just better technology. It will require a fundamental change in how we think about space. For astronauts aboard the International Space Station, space debris isn't an abstract threat. It's a daily reality that shapes every aspect of their lives in orbit. The station operates in one of the most debris-dense regions of space. Low Earth orbit between 250 and 400 miles above Earth. Every few months, sometimes more often, the station's crew receives an urgent message from Mission Control. Debris is approaching, and they need to take shelter immediately. The crew quickly gathers in the Russian Soyuz spacecraft that serves as their lifeboat, seals the hatches, and waits. If the debris strikes the station and causes a catastrophic decompression, they can undock and return to Earth. If they're lucky, the debris misses, and they can return to their normal activities. These debris avoidance maneuvers, or DAMs, have become routine. Since the station began operations in 2000, there have been over 30 occasions when the crew has had to shelter in place because of approaching debris. Several times, the entire station has had to fire its thrusters to move out of the way of particularly dangerous pieces. The psychological impact on the crew is significant. Imagine trying to conduct scientific experiments or maintain complex systems, while knowing that at any moment, a piece of debris the size of a marble could punch through the hull and kill everyone aboard. The crew trains extensively for emergency situations, but there's no training that can completely eliminate the stress of living under constant threat. The station itself shows the scars of its debris encounters. The cupola, a 7-windowed observatory module where astronauts can watch Earth pass below, has been struck by debris multiple times. The impacts have left small chips and cracks in the windows. While these strikes haven't been catastrophic, they serve as constant reminders of the hostile environment the station operates in. In 2016, astronaut Tim Peake noticed a circular chip in one of the cupola's windows that was about 7 millimeters across. Analysis by engineers on the ground determined that it had been caused by a piece of debris smaller than 1/1000th of an inch in diameter, probably a tiny fragment of paint or metal that had been traveling at orbital velocity. The fact that such a minuscule piece of debris could damage the station's windows highlights just how dangerous the space environment has become. The windows are made of multiple layers of specially designed glass and aluminum oxynitride, essentially transparent aluminum, specifically to resist debris impacts. Yet even this advanced protection can be overwhelmed by high-speed impacts. The station's hull is protected by Whipple shields, named after astronomer Fred Whipple, who first proposed the design. These shields consist of multiple layers of material spaced apart, so that incoming debris hits the outer layer first, breaks apart, and dissipates its energy before reaching the pressure hull. The shields are effective against small debris, but they have limits. Larger pieces of debris, anything bigger than about 1/2 inch in diameter, could potentially penetrate the shields and cause catastrophic damage. For these threats, the only defense is avoidance. When ground-based radar detects a large piece of debris on a collision course with the station, Mission Control calculates a maneuver to move the station out of the way. These maneuvers are carefully planned operations that require hours or days of preparation. The station's Russian Progress cargo spacecraft, or the station's own thrusters, fire for several minutes to change the station's orbit slightly, typically by just a few hundred meters. It sounds simple, but in the precise environment of orbital mechanics, even small changes require extensive calculation to ensure they don't create new problems. Sometimes, though, there isn't enough time for a maneuver. If debris is detected too late, or if the tracking data is too uncertain to plan a safe maneuver, the crew has no choice but to shelter in place and hope for the best. These emergency shelters are among the most stressful experiences astronauts face. The crew typically receives just a few hours warning, sometimes less. They quickly secure any dangerous equipment, gather essential supplies, and retreat to the Soyuz spacecraft. Then they wait, strapped into their seats, listening to the radio chatter from mission control as the debris approaches. The closest call in the station's history came in March 2012, when a piece of debris from a Russian satellite passed within just a few hundred meters of the station. The crew had been ordered to take shelter, and for several tense minutes, nobody knew if the debris would hit. It missed, but the margin was uncomfortably small. That incident highlighted a disturbing trend. Debris encounters are becoming more frequent. In the early years of the station's operation, debris shelters were rare events, happening perhaps once or twice a year. Now they occur several times a year, sometimes multiple times in a single month. The increasing frequency of these events is taking a toll on the station's operations. Each time the crew has to take shelter, normal activities are suspended. Scientific experiments are put on hold, maintenance tasks are delayed, and the crew's schedules are disrupted. Over time, these interruptions add up to significant lost productivity. More worrying is the psychological impact on the crew. Living under constant threat of random, violent death is not something human beings are designed to handle well. While astronauts are selected and trained for their psychological resilience, the stress of repeated debris encounters can accumulate over long missions. Some astronauts have reported that the threat of debris has changed how they think about their work in space. Instead of feeling like explorers pushing the boundaries of human knowledge, they sometimes feel like they're living in a cosmic war zone, constantly under threat from an invisible enemy. The debris threat also affects the design and operation of future spacecraft. NASA's new Orion spacecraft, designed for missions to the Moon and Mars, includes enhanced debris protection and improved crew shelters. Commercial crew vehicles like SpaceX's Dragon and Boeing's Starliner are also designed with debris threats in mind. But these defensive measures come at a cost. Every pound of debris shielding is a pound that can't be used for scientific equipment, supplies, or crew comfort. As the debris threat grows, spacecraft will need more and more protection, leaving less room for their actual missions. The debris threat is also affecting the selection of orbits for new missions. Mission planners now have to consider not just the scientific or operational requirements of a mission, but also the debris environment in different orbital regions. Some otherwise attractive orbits are avoided because they're too dangerous. This is already constraining human spaceflight operations. The International Space Station operates at a relatively low altitude, partly to minimize its exposure to debris. Higher orbits would offer some operational advantages, but they also contain more dangerous debris. As we plan for future human missions to the Moon and Mars, the debris threat in low Earth orbit becomes a significant concern. Spacecraft traveling to other worlds must pass through the most debris-dense regions of space during launch and return. Each passage is a dangerous gamble that could end the mission before it really begins. The cruel irony is that the more successful we become at space exploration, the more dangerous space becomes for future explorers. Every satellite we launch, every mission we conduct, adds to the debris population and increases the threat to future missions. This feedback loop is one of the most troubling aspects of the debris crisis. Unlike other environmental problems, where the damage is gradual and can potentially be reversed, space debris creates a situation where our past successes actively undermine our future possibilities. For astronauts, this creates a peculiar form of existential anxiety. They're pursuing humanity's greatest adventure, while simultaneously helping to make that adventure more dangerous for future generations. It's a burden that weighs heavily on many of those who have seen Earth from space and understand both the beauty and fragility of our position in the cosmos. While astronauts face the most immediate physical danger from space debris, the threat extends far beyond the few hundred people who have traveled to space. For billions of people on Earth, space debris represents a largely invisible but increasingly critical threat to the technological infrastructure that modern civilization depends on. Consider your smartphone. Right now, as you listen to this, your phone is almost certainly communicating with satellites in space. When you use GPS to navigate, your phone is receiving signals from a constellation of satellites 20,000 kilometers above Earth. When you check the weather, you're seeing data collected by meteorological satellites. When you make a phone call or send a text message in a remote area, your signal may be routed through communication satellites. All of these satellites operate in an environment that's becoming increasingly hostile due to space debris. Every satellite in orbit is potentially just one collision away from being destroyed, taking with it the services that millions of people rely on. The economic implications are staggering. The global satellite industry generates over $300 billion in revenue annually. This includes direct satellite services like television broadcasting and satellite phone calls, but also the indirect economic benefits of satellite-enabled services like GPS-guided agriculture, satellite weather forecasting, and satellite-based internet access. GPS alone is estimated to generate over $1 trillion in economic benefits annually in the United States. The system enables precision agriculture that increases crop yields and reduces fertilizer use. It allows airlines to fly more efficient routes, saving fuel and reducing emissions. It enables ride-sharing services, delivery companies, and emergency responders to navigate efficiently. If space debris were to significantly damage or destroy the GPS constellation, the economic disruption would be immediate and severe. Ships and aircraft would have to return to older, less efficient navigation methods. Precision agriculture would become impossible, potentially reducing crop yields at a time when global food security is already a concern. The power grid would also be affected. Many electrical utilities use GPS signals to synchronize their operations with incredible precision. Losing GPS would make the power grid less efficient and potentially less stable. Financial markets, which rely on GPS for time-stamping transactions, would face significant operational challenges. But GPS is just one example. Weather satellites provide early warning of hurricanes, tornadoes, and other severe weather events. They allow meteorologists to track storms with precision that saves thousands of lives every year. They also provide the data that makes medium and long-range weather forecasting possible. Earth observation satellites monitor deforestation, track the effects of climate change, and provide early warning of natural disasters. like wildfires and volcanic eruptions. They enable scientists to study changes in ice coverage, sea level, and atmospheric composition. Without these satellites, our understanding of how Earth's climate is changing would be severely limited. Communication satellites carry phone calls, internet traffic, and television signals to remote areas where terrestrial infrastructure is impractical or too expensive. For isolated communities, satellite communication may be the only reliable link to the outside world. Satellite internet is also becoming increasingly important for providing broadband access to rural areas. The threat that space debris poses to these systems is not theoretical. In 2013, a small piece of debris struck the European Space Agency's Sentinel-1A Earth observation satellite. The impact created a small crater in one of the satellite's solar panels and slightly reduced its power generation capability. While the satellite continued to operate, the incident demonstrated that even small pieces of debris can cause significant damage. In 2019, the European Space Agency had to perform an emergency maneuver to move one of its satellites out of the path of a SpaceX Starlink satellite. While this wasn't debris in the traditional sense, it highlighted how the increasing congestion in space is making collision avoidance more challenging and more common. The Starlink incident also revealed gaps in the current system for coordinating satellite operations. SpaceX had been planning to maneuver their satellite out of the way, but a problem with their automated system prevented the maneuver from being executed. The European Space Agency only learned about this at the last minute and had to quickly implement their own avoidance maneuver. As the number of satellites in orbit continues to grow, these types of close calls are becoming more common. Companies like SpaceX, Amazon, and OneWeb are planning to launch thousands of new satellites over the next decade to provide global internet coverage. Each of these satellites represents a potential source of debris if something goes wrong. The planned satellite constellations also create new challenges for debris tracking and collision avoidance. Current space surveillance systems were designed to track a few thousand objects, managing tens of thousands of satellites. Plus, all the debris they might create will require significant upgrades to ground-based tracking systems. The increasing commercial activity in space is also changing the economics of satellite operations. Traditional satellites were expensive, government-funded projects with lifespans measured in decades. Many of the new commercial satellites are designed to be cheaper and have shorter operational lives, sometimes just a few years. This shift toward shorter-lived, cheaper satellites has both positive and negative implications for the debris problem. On the positive side, satellites with shorter operational lives spend less time in orbit and are less likely to fail and create debris. On the negative side, the shorter lifespans mean that more satellites need to be launched to maintain the same level of service, increasing the overall number of objects in orbit. The commercial space industry is also driving innovation in debris mitigation technologies. Companies are developing satellites with improved propulsion systems for end-of-life disposal, better tracking and communication systems to avoid collisions, and designs that are less likely to create dangerous debris if they do break apart. But market forces don't always align with debris mitigation. Building satellites that are less likely to create debris often makes them more expensive. Installing better propulsion systems for end-of-life disposal adds weight and cost. For commercial companies operating on tight margins, these additional costs can make the difference between a profitable and unprofitable business. This creates a classic tragedy of the commons scenario. Each individual satellite operator has an incentive to minimize their costs, even if that means creating slightly more debris risk. But when all operators follow this logic, the cumulative effect is a significant increase in the overall debris threat. Regulatory agencies are trying to address this through increasingly strict licensing requirements for satellite operations. In the United States, the Federal Communications Commission now requires satellite operators to demonstrate that they have a viable plan for disposing of their satellites at the end of their missions, but enforcement remains challenging, particularly for international operators. Space debris is a global problem that requires global solutions, but international law and space governance structures were designed for an era when only a few government agencies operated in space. The emergence of commercial space activities has created new actors with different incentives and capabilities than traditional government space agencies. Some commercial operators have embraced debris mitigation as a competitive advantage, marketing their satellites as more environmentally responsible than their competitors. Others have been less proactive, viewing debris mitigation as an unnecessary cost. This patchwork of different approaches and standards is creating an increasingly complex and potentially unstable situation in orbit. As more countries and companies enter the space business, the challenge of coordinating debris mitigation efforts will only become more difficult. The stakes couldn't be higher. The satellite services that we increasingly depend on are operating in an environment that's becoming more dangerous every day. Each successful satellite launch is a small victory for human technological achievement, but also a contribution to a problem that could eventually make such launches impossible. We're essentially conducting a vast, uncontrolled experiment with the space environment that supports our technological civilization. The outcome of that experiment will determine whether space remains a resource for human development or becomes an inaccessible wasteland of high-speed debris. The story of how we got into this predicament is largely a story of good intentions and short-term thinking. For decades, space agencies and companies focused on the immediate challenges of getting satellites into orbit and making them work once they were there. The long-term consequences of leaving dead satellites and rocket stages in orbit seemed like a problem for future generations to solve. This short-sightedness was perhaps understandable in the early days of the space age. Launching satellites was enormously difficult and expensive, and mission success was far from guaranteed. It made sense to focus on the immediate challenges rather than worry about what would happen to the satellite decades later. But as satellite technology matured and launch costs decreased, the attitude should have changed. By the 1980s and 90s, it was clear that space debris was becoming a serious problem. Yet the industry continued to operate under the assumption that space was vast enough to absorb whatever we put into it. This assumption was based on a fundamental misunderstanding of orbital mechanics. While space as a whole is indeed vast, the useful orbital regions around Earth are relatively small and constrained. Low Earth orbit, where most satellites operate, is like a thin shell around our planet. The volume of this shell is large compared to Earth's surface, but small compared to the volume of space as a whole. Moreover, not all parts of this orbital shell are equally useful. Satellites need to be in specific orbits to perform their functions. Communication satellites work best in geostationary orbit, 22,000 miles above the equator. Earth observation satellites need to be in polar orbits that carry them over every part of Earth's surface. GPS satellites operate in medium Earth orbit at a precise altitude that allows them to maintain their constellation geometry, These constraints mean that satellites tend to cluster in relatively small regions of space, dramatically increasing the likelihood of collisions. It's not like a vast ocean where ships can spread out to avoid each other. It's more like a complex highway system, where all the traffic has to flow through a few critical interchanges. The highway analogy is apt in another way. Like highways, orbital regions have carrying capacities. A highway can safely accommodate a certain number of vehicles traveling at certain speeds. Beyond that capacity, traffic becomes congested and accidents become more likely. In space, we've been steadily increasing the traffic density without investing in better traffic control systems. Until recently, there was no Space Traffic Control Authority, no standardized collision avoidance procedures, and no real-time communication system for coordinating satellite movements. The result is that we've created a situation where thousands of high-value spacecraft are operating in close proximity with minimal coordination and limited ability to avoid each other. It's a recipe for disaster that has already resulted in several major collisions and countless near misses. The problem is compounded by the fact that many of the objects in orbit are no longer under active control. Dead satellites, spent rocket stages, and pieces of debris follow predictable but uncontrollable orbits. They can't maneuver to avoid collisions, and they can't respond to commands from the ground. This creates a situation where active satellites have to maneuver around an ever-growing population of orbital obstacles. As the number of these obstacles increases, the burden on active satellites to avoid them becomes greater. Eventually, collision avoidance maneuvers become so frequent that they interfere with normal satellite operations. We're already seeing this effect with the International Space Station, which has had to perform increasingly frequent debris avoidance maneuvers. Each maneuver uses fuel, disrupts crew activities, and slightly alters the station's orbit in ways that can affect future operations. For commercial satellite operators, frequent collision avoidance maneuvers create both operational and economic challenges. Maneuvers use fuel, which limits the satellite's operational lifetime. They also disrupt service, potentially causing missed communications or gaps in coverage. The economic calculations are complex. Is it better to risk a collision, which might destroy a $100 million satellite, but has a low probability of occurring? Or is it better to perform frequent avoidance maneuvers, which have a small but certain cost, and gradually degrade the satellite's performance? Different operators are making different choices, creating an inconsistent patchwork of risk management approaches. Some satellites are maneuvered aggressively to avoid even small debris threats. Others are left in their original orbits unless the collision probability exceeds a certain threshold. This inconsistency creates additional coordination challenges. When two satellites are on a collision course, which one should maneuver? If both operators decide to maneuver, they might inadvertently increase the collision risk. If neither maneuvers, a collision becomes certain. International guidelines recommend that satellite operators coordinate their collision avoidance efforts. But these guidelines are not legally binding, and enforcement mechanisms are limited. The result is an ad hoc system that relies heavily on good faith cooperation between operators who may be commercial competitors. The system has worked reasonably well so far, but it's under increasing strain as the number of satellites and debris objects continues to grow. Each new object in orbit makes the coordination problem slightly more complex, and the margin for error continues to shrink. Looking toward the future, the challenges will only become more severe. Plans for large satellite constellations envision tens of thousands of new satellites in the next decade. Managing collision avoidance for such a large population of objects will require fundamental advances in space traffic management systems. Some experts argue that we need to move beyond the current ad hoc system towards something more like an air traffic control system for space. Such a system would track all objects in orbit, predict collisions well in advance, and coordinate avoidance maneuvers to minimize fuel consumption and service disruptions. But creating such a system faces enormous technical and political challenges. Unlike aviation, where aircraft operate within national airspace under clear regulatory authority, space is an international commons with no single governing authority. Different countries have different space surveillance capabilities and different approaches to sharing tracking data. Some information about satellite positions and maneuvers is considered sensitive for national security reasons. Building an effective space traffic control system will require unprecedented levels of international cooperation and data sharing. Even if these political challenges can be overcome, the technical challenges are daunting. Current space surveillance systems can track objects larger than about 4 inches, but smaller pieces of debris are numerous and dangerous. A comprehensive space traffic control system would need to track millions of objects simultaneously and predict their positions with extraordinary accuracy. The computational requirements for such a system would be enormous. Calculating collision probabilities for thousands of objects over periods of days or weeks requires solving complex orbital mechanics problems millions of times. Current computer systems can barely handle this workload for the existing population of tracked objects. As the object population grows, the computational burden will grow even faster. The number of potential collision pairs increases roughly as the square of the object population. Double the number of objects, and you quadruple the number of collision calculations that need to be performed. This scaling problem means that our current approaches to space traffic management will become inadequate long before the satellite population reaches the levels envisioned by commercial constellation operators. We need not just incremental improvements in tracking and coordination, but fundamental breakthroughs in how we manage the space environment. The alternative is a gradual slide toward chaos in orbit, where collision avoidance becomes so complex and fuel-intensive that many satellite operations become uneconomical. In that scenario, space would effectively become unusable, not because of a dramatic cascade of collisions, but because of the accumulated burden of managing an overcrowded orbital environment. Either way, whether through sudden catastrophe or gradual degradation, the current trajectory is unsustainable. We're approaching a crossroads where we must either develop fundamentally new approaches to space traffic management or accept that space will become increasingly inaccessible to human activities. The military implications of space debris extend far beyond the immediate threat to individual satellites. For modern military forces, space-based assets are not just helpful supplements to terrestrial capabilities, they're essential infrastructure that enables everything from precision-guided munitions to secure communications to real-time intelligence gathering. The United States military, which operates the world's most space-dependent military force, has identified space superiority as critical to national security. Military satellites provide GPS navigation for everything from aircraft and ships to individual soldiers on the ground. They carry encrypted communications that can't be intercepted by enemies. They provide real-time surveillance of potential threats around the world. Losing these capabilities would fundamentally alter how modern warfare is conducted. Without GPS, precision-guided weapons become far less accurate. Without satellite communications, coordinating operations across multiple theaters becomes much more difficult. Without satellite surveillance, military commanders lose critical intelligence about enemy movements and capabilities. The vulnerability of space assets to debris, therefore, represents a significant national security concern. A single piece of debris could disable a critical military satellite, potentially affecting military operations around the world. Multiple debris impacts could degrade military space capabilities to the point where they seriously affect a nation's ability to defend itself. This vulnerability is particularly concerning because space debris is an indiscriminate threat. Unlike traditional military threats that can be deterred or defended against, debris strikes are essentially random events that can't be predicted or prevented with certainty. A nation could lose critical military capabilities, not through enemy action, but through the accumulated effects of decades of poor space environmental management. The military implications of debris go beyond just the threat to existing satellites. The debris environment also affects the ability to launch new military satellites or replace ones that have been damaged or destroyed. If launch windows become constrained by debris threats, or if certain orbits become too dangerous to use, military space capabilities could be significantly degraded. This has led to increased military interest in space situational awareness, the ability to track and predict the positions of objects in space. The United States Space Force operates a network of ground-based radars and optical telescopes that monitor space for debris and other threats. This information is shared with satellite operators around the world to help them avoid collisions. But the military space surveillance capabilities are being stretched thin by the growing debris population. Tracking 34,000 objects with sufficient accuracy to predict collisions days in advance requires enormous computational resources and constant attention. As the debris population grows, maintaining this level of surveillance awareness becomes increasingly challenging. There's also growing concern about the potential for adversaries to weaponize the debris problem. Anti-satellite weapons that create large amounts of debris, like the Chinese test in 2007, don't just destroy their immediate targets. They create long-lasting hazards that threaten all satellites in similar orbits, including those belonging to neutral countries. This type of indiscriminate debris creation could be used as a form of area denial weapon, making certain orbital regions too dangerous for anyone to use. An adversary might calculate that creating a debris field in a critical orbital region would harm their enemy's space capabilities more than their own, even if their own satellites were also at risk. The prospect of deliberate debris creation as a military tactic has led to discussions about treating such actions as violations of international law. Some experts argue that creating large amounts of space debris should be considered an environmental war crime, similar to deliberately poisoning a river or releasing biological weapons. But international law in space is still evolving, and enforcement mechanisms are limited. Unlike terrestrial environmental crimes, which can be prosecuted by international courts, space environmental crimes would be difficult to investigate and prosecute. The evidence would be scattered across hundreds of miles of orbital space, and determining intent would be challenging. The military is also concerned about the potential for space debris to mask deliberate attacks on satellites. If a military satellite is destroyed by debris, it might be difficult to determine whether the impact was accidental or whether the debris had been deliberately maneuvered to cause a collision. This ambiguity could complicate military decision-making in crisis situations. If a critical military satellite is lost during a period of international tension, How can commanders determine whether it was an accident or an act of war? The wrong conclusion could lead to inappropriate escalation or failure to respond to actual attacks. To address these concerns, military space surveillance systems are being upgraded to provide better tracking and characterization of space objects. New radar systems and optical telescopes are being deployed to improve the ability to detect and track smaller pieces of debris. Advanced computer algorithms are being developed to better predict collision probabilities and distinguish between natural debris and potentially threatening objects. The military is also investing in more resilient satellite architectures. Instead of relying on a few large, expensive satellites, military planners are moving toward larger numbers of smaller, cheaper satellites that can provide redundant coverage. If one satellite is lost to debris or enemy action, others can continue to provide service. This approach, known as disaggregated architecture, makes military space systems more resilient, but also contributes to the debris problem by putting more objects in orbit. It's another example of how responses to the debris threat can sometimes exacerbate the underlying problem. The military is also developing rapid satellite replacement capabilities. Instead of waiting years to build and launch replacement satellites, military space systems of the future may be able to launch replacements within days or weeks of losing a satellite. This reduces the impact of debris strikes but requires maintaining large numbers of spare satellites and launch vehicles. All of these military responses to the debris threat represent significant investments in space capabilities. The cost of making military space systems resilient to debris threats is measured in tens of billions of dollars, money that might otherwise be spent on other military capabilities or civilian programs. But military planners argue that these investments are necessary to maintain military effectiveness in an environment where space assets are increasingly critical and increasingly vulnerable. The alternative, accepting that military space capabilities could be randomly degraded by debris strikes, is seen as unacceptable risk to national security. The international nature of the debris threat also complicates military planning. Space debris doesn't respect national boundaries, and debris created by one country's satellites or anti-satellite tests can threaten other countries' military satellites. This creates complex questions about responsibility and liability for debris-related damage. If debris from a Chinese satellite destroys an American military satellite, is that an act of aggression or an unfortunate accident? Should the Chinese government be held liable for the damage? These questions don't have clear answers under current international law, but they could become critical issues as debris-related incidents become more common. The military implications of space debris therefore extend beyond immediate operational concerns to fundamental questions about space governance, international law, and the future of space as a domain for military activity. How these questions are resolved will shape not just military space capabilities, but the broader future of human activities in space. As the debris problem has grown more severe, the international community has gradually developed a complex web of guidelines, agreements, and monitoring systems designed to limit the creation of new debris and mitigate the risks posed by existing debris. However, these efforts have been hampered by the lack of binding international law and enforcement mechanisms. The first major international effort to address space debris came in 1995, when the Interagency Space Debris Coordination Committee was established. This group, which includes space agencies from the United States, Russia, Europe, Japan, China, India, and other countries, developed technical guidelines for limiting the creation of new debris. The IADC guidelines recommend that satellite operators plan for the disposal of their spacecraft at the end of their missions, either by bringing them back to Earth or moving them to graveyard orbits where they won't interfere with active satellites. The guidelines also recommend designing spacecraft to minimize the risk of explosions or breakups that could create large amounts of debris. These guidelines were later incorporated into the United Nations Space Debris Mitigation Guidelines, adopted by the UN Committee on the Peaceful Uses of Outer Space in 2007. The UN guidelines represent the broadest international consensus on space debris mitigation, but they remain non-binding recommendations rather than enforceable law. The challenge of enforcing space debris mitigation measures is fundamentally different from other environmental problems. Unlike terrestrial pollution, where the damage is typically visible and can be traced to specific sources, space debris is largely invisible from Earth, and its sources are often unclear. When a piece of debris damages a satellite, it's often impossible to determine where the debris came from. Even if the debris can be tracked back to a specific satellite or rocket launch, that launch may have occurred decades ago under different management or ownership. The original operators may no longer exist, or they may argue that the debris creation was unintentional and therefore not their responsibility. The legal framework for space activities, established primarily through the Outer Space Treaty of 1967, was designed for an era when only government agencies operated in space. The treaty makes countries responsible for the activities of their nationals in space, but it doesn't clearly address liability for debris creation or cleanup obligations. As commercial space activities have expanded, the legal framework has become increasingly inadequate. Commercial companies may operate under loose regulatory oversight, and their financial liability for debris creation is often limited. If a commercial satellite breaks apart and creates dangerous debris, the cleanup costs could exceed the company's assets, leaving the problem for governments or other satellite operators to address. Some countries have begun to strengthen their national space regulations to address debris concerns. The United States has updated its licensing requirements for commercial satellites to include detailed debris mitigation plans. France has imposed liability requirements on satellite operators to cover potential debris cleanup costs. But these national approaches create a patchwork of different standards and requirements that may not be effective in addressing a global problem. A satellite operator could potentially avoid strict debris mitigation requirements by licensing their satellite in a country with weaker regulations. The European Space Agency has taken a leading role in developing debris removal technologies and advocating for stronger international cooperation on debris issues. The agency's Clean Space Initiative is developing technologies for active debris removal and is planning the world's first commercial debris removal mission. Japan has also been active in debris mitigation research, developing innovative technologies like electrodynamic tethers that can use Earth's magnetic field to drag debris out of orbit. The Japanese Space Agency has tested these technologies on several missions and is working to make them commercially viable. China, despite being responsible for the largest single debris creation event in history, has become increasingly engaged in international debris mitigation efforts. Chinese officials now participate in international debris coordination meetings and have committed to following international guidelines for future missions. However, some experts argue that voluntary guidelines and national regulations are insufficient to address the scale of the debris problem. They call for binding international treaties that would create enforceable obligations for debris mitigation and cleanup, with financial penalties for countries or companies that fail to comply. Negotiating such treaties would be extremely challenging. Countries would need to agree on technical standards for spacecraft design and operations, liability rules for debris creation, and funding mechanisms for cleanup efforts. They would also need to create international institutions with the authority to monitor compliance and impose penalties. The precedent of international environmental treaties offers some hope for progress. The Montreal Protocol, which successfully addressed the depletion of Earth's ozone layer, demonstrated that countries can cooperate to address global environmental threats when the scientific evidence is clear and the economic costs of inaction are high. The space debris problem shares many characteristics with ozone depletion. The threat is global, affects all countries, and requires coordinated international action to address. The scientific evidence for the problem is clear, and the potential costs of inaction are enormous. However, space activities are more strategically sensitive than the industrial chemicals that were regulated under the Montreal Protocol. Space capabilities are closely tied to national security, and countries may be reluctant to accept international oversight of their space activities. The commercial space industry also presents new challenges for international regulation. Unlike government space agencies, which are directly accountable to their governments, commercial companies may have incentives that don't align with debris mitigation goals. Some companies have embraced debris mitigation as a competitive advantage, marketing their satellites as more environmentally responsible than those of their competitors. Others have been more focused on minimizing costs and may view debris mitigation requirements as burdensome regulations. The rapid growth of the commercial space industry has outpaced the development of regulatory frameworks in many countries. New companies are launching satellites faster than regulators can develop and implement appropriate oversight mechanisms. International cooperation on space debris is further complicated by the dual-use nature of many space technologies. Technologies developed for debris removal could potentially be used as anti-satellite weapons. Countries may be reluctant to share information about their space surveillance capabilities because that information could be used to target their satellites. Despite these challenges, there are signs of progress. The number of countries participating in international space debris coordination efforts has grown steadily. Space agencies are increasingly sharing tracking data and coordinating collision avoidance efforts. Commercial companies are beginning to factor debris mitigation into their business plans. The urgency of the problem is also driving innovation in debris mitigation technologies. New spacecraft designs incorporate improved systems for end-of-life disposal. Launch providers are developing upper stages that can restart their engines multiple times to place payloads in precise orbits and then deorbit themselves. But experts warn that these incremental improvements may not be sufficient to prevent the Kessler syndrome. The debris population is growing faster than mitigation efforts can reduce it, and the risk of catastrophic cascading collisions continues to increase. Some scientists argue that the international community needs to treat space debris as a true emergency, similar to climate change or nuclear proliferation. They call for urgent, coordinated action to address the problem before it becomes irreversible. Others are more optimistic, arguing that market forces and technological innovation will eventually solve the debris problem. They point to the development of reusable rockets, which reduce the amount of debris created per launch, and the growing commercial interest in debris removal services. The truth probably lies somewhere between these extremes. The debris problem is serious and urgent, but it's not insurmountable. With appropriate international cooperation, technological innovation, and regulatory frameworks, it should be possible to manage the debris population and prevent catastrophic cascading collisions. However, achieving this will require overcoming significant technical, economic, and political challenges. The international community will need to develop new forms of cooperation and governance that are adapted to the unique characteristics of space activities. The stakes are high. Failure to address the debris problem could effectively end human expansion into space for generations. Success could enable continued growth in space activities while preserving the space environment for future generations. The choices made in the next decade will likely determine which of these futures becomes reality. The space debris crisis has sparked remarkable innovation in cleanup technologies as engineers and entrepreneurs around the world work to develop practical solutions for removing dangerous objects from orbit. These efforts range from relatively simple mechanical systems to advanced autonomous spacecraft that can hunt down and capture debris. One of the most promising approaches involves using robotic spacecraft equipped with various capture mechanisms. The European Space Agency's ClearSpace 1 mission, scheduled for launch in 2025, will demonstrate key technologies for active debris removal. The spacecraft will use robotic arms to capture a piece of debris and then deorbit both itself and the target, burning up safely in Earth's atmosphere. The target for ClearSpace 1 is a carefully chosen piece of debris, the upper stage of a rocket that launched a cluster of small satellites in 2013. The object weighs about 250 pounds and is roughly the size of a small car. While not enormous by satellite standards, it represents exactly the type of large debris that poses the greatest collision risk. The mission faces significant technical challenges. The target object is tumbling unpredictably, has no active guidance or communication systems, and was never designed to be captured by another spacecraft. ClearSpace 1 will need to approach the debris carefully, match its rotation, and grab it securely without causing it to break apart. If successful, the mission will demonstrate that active debris removal is technically feasible, but it will also highlight the economic challenges. ClearSpace 1 costs over $100 million to remove a single piece of debris. At that price, cleaning up even a small fraction of the existing debris population would cost trillions of dollars. Other organizations are developing alternative approaches that might be more cost-effective. The Japanese Space Agency has experimented with electrodynamic tethers, long-conducting cables that can interact with Earth's magnetic field to change a spacecraft's orbit. By deploying a tether, a piece of debris could theoretically be made to spiral down into Earth's atmosphere without requiring a separate removal spacecraft. The challenge with tethers is deploying them on objects that weren't designed to accommodate them. Most debris pieces lack the attachment points, power systems, or communication capabilities needed to deploy a tether. The technology works well for new satellites designed with tethers in mind. But retrofitting existing debris is much more difficult. Laser systems represent another potential approach to debris removal. Ground-based or space-based lasers could theoretically heat one side of a debris piece, causing material to vaporize and creating a small thrust that gradually changes the object's orbit. With enough time and energy, this photon pressure could push debris into Earth's atmosphere. Several research groups have tested laser debris removal concepts in laboratory settings, and the physics appears sound. However, the power requirements are enormous. and the precision needed to track and target small debris pieces over long periods is beyond current capabilities. There are also political and safety concerns about powerful laser systems that could potentially target satellites. Any laser system capable of removing debris would also be capable of disabling or destroying functional satellites, making it essentially a space weapon. Harpoon systems offer a more mechanical approach to debris capture. A spacecraft could fire a harpoon into a piece of debris, then reel it in with a cable, or use the connection to change the debris's orbit. The European Space Agency has tested harpoon systems in space, successfully demonstrating that they can penetrate typical spacecraft materials. The challenge with harpoons is ensuring that the impact doesn't create additional debris fragments. If the harpoon impact causes the target to break apart, the removal effort could actually make the debris problem worse. This requires careful design of both the harpoon itself and the targeting system. Net-based capture systems have also been tested in space. These systems deploy large nets that can ensnare debris pieces, then use thrusters to change the combined orbit of the net and debris. Nets have the advantage of being able to capture irregularly shaped objects and multiple pieces of debris simultaneously. However, nets face their own challenges. They need to be large enough to reliably capture tumbling debris, but large nets are difficult to deploy accurately and control precisely. There's also the risk that a net could become tangled with other spacecraft or debris, creating new problems. Some of the most innovative debris removal concepts involve autonomous swarms of small spacecraft. These systems would deploy large numbers of small, inexpensive robots that could work together to identify, approach, and capture debris pieces. Each robot might be capable of removing only small debris, but working together, they could potentially address the millions of small fragments that pose collision risks. Swarm systems could be more cost-effective than large, complex debris removal spacecraft because they could be mass-produced using standardized components. They could also be more resilient because the loss of individual robots wouldn't compromise the entire mission. The technical challenges for swarm systems are formidable. Each robot needs to be capable of autonomous navigation, target identification, and capture operations. They need to coordinate their activities to avoid interfering with each other. And they need to be reliable enough to operate for months or years in the harsh environment of space. Despite the technical innovations, all active debris removal systems face fundamental economic challenges. The cost of removing debris is typically much higher than the cost of the original satellite that created the debris. This creates a perverse economic incentive where it's cheaper to launch new satellites and accept debris risks than to clean up existing debris. Some experts argue that debris removal will only become economically viable when the costs of debris-related damage exceed the costs of cleanup. That might happen if collision rates increase dramatically, making satellite insurance unaffordable, or forcing satellite operators to invest heavily in defensive measures. Others believe that regulatory requirements will drive the debris removal market. If governments require satellite operators to clean up their debris, or if liability rules make operators financially responsible for debris-related damage, commercial debris removal services could become profitable. The emerging commercial space economy might also change the economics of debris removal. As launch costs continue to decrease and satellite manufacturing becomes more automated, it might become cost-effective to launch dedicated debris removal missions that can clean up multiple pieces of debris per mission. Some companies are already planning commercial debris removal services, These ventures typically focus on high-value targets, like large defunct satellites in valuable orbital slots. By removing one large satellite, they can free up orbital real estate that can be used for new satellites worth hundreds of millions of dollars. The insurance industry is also beginning to factor debris risks into satellite insurance policies. As debris-related losses mount, insurance premiums for satellites in high-risk orbital regions are increasing. This creates economic pressure for satellite operators to either avoid debris-heavy orbits or invest in debris mitigation measures. International cooperation will be essential for large-scale debris removal efforts. No single country or company has the resources to address the entire debris population alone. Sharing costs and technologies across multiple nations and organizations could make debris removal more affordable and effective. However, international cooperation on debris removal faces the same challenges as other space governance issues. Countries may be reluctant to share sensitive space technologies or allow foreign spacecraft to approach their satellites or debris. There are also complex legal questions about removing debris that technically belongs to other countries. International law requires permission before interfering with another country's space objects, even if those objects are dangerous debris. Negotiating these permissions could significantly complicate debris removal efforts. Despite these challenges, progress is being made. The first commercial debris removal missions are expected to launch within the next few years. These missions will provide valuable experience and help drive down the costs of future removal efforts. Whether debris removal technologies can be scaled up quickly enough to address the growing debris population remains to be seen. The window for action may be closing as the debris population approaches critical levels that could trigger cascading collisions. But the innovation and investment flowing into debris removal technologies represent humanity's best hope for preserving access to space for future generations. Success will require not just technical breakthroughs, but also new forms of international cooperation and economic organization. The race is on between the growing debris population and our ability to clean it up. The outcome will determine whether space remains open for human exploration and development or becomes an inaccessible wasteland of high-speed projectiles. The long-term implications of the space debris crisis extend far beyond the immediate risks to existing satellites and space missions. At stake is nothing less than humanity's future as a spacefaring civilization. The choices we make about debris mitigation and cleanup in the next decade could determine whether our species remains trapped on Earth or continues expanding into the solar system. Consider the cascade of consequences that could follow from a severe debris cascade in low Earth orbit. Such an event wouldn't just affect satellite communications and GPS navigation. It would fundamentally alter humanity's relationship with space and our ability to explore beyond Earth. If low Earth orbit becomes too dangerous for satellite operations, the economic damage would be measured in trillions of dollars. But the secondary effects might be even more significant. Space-based Earth observation, which is critical for climate monitoring and disaster response, would be severely compromised. Just as climate change makes such monitoring more important than ever, the scientific consequences would be equally severe. Space-based astronomy has revolutionized our understanding of the universe. From the discovery of exoplanets to detailed observations of distant galaxies. If debris makes it impossible to maintain space telescopes, astronomical research would be set back by decades. Human spaceflight would face even greater challenges. The International Space Station operates in the most debris-dense region of space, A severe debris cascade could make it impossible to safely supply the station or transport crews to and from orbit. The station might have to be abandoned, ending 2 decades of continuous human presence in space. Future human missions to the Moon and Mars would also be affected. Spacecraft traveling to other worlds must pass through low Earth orbit during launch and return. If this region becomes too dangerous to transit, interplanetary travel could become prohibitively risky. The debris crisis could also affect the development of space-based solar power, which many scientists see as essential for addressing climate change. Large solar power satellites would require extensive construction and maintenance activities in space. If debris makes such activities too dangerous, this potential solution to Earth's energy needs might never be realized. Commercial space activities that are just beginning to flourish could be stillborn. Space tourism, asteroid mining, and orbital manufacturing all depend on reliable access to space. A severe debris crisis could kill these industries before they fully develop, eliminating potentially enormous economic opportunities. The geopolitical implications are equally concerning. Space capabilities have become essential for modern military forces and are increasingly important for national prestige and soft power. Countries that lose their space capabilities due to debris would find themselves at significant disadvantages relative to nations with more protected space assets. This could lead to a new form of international inequality, where space-capable nations enjoy enormous advantages in economic development, scientific research, and military power. Such disparities could become sources of international tension and conflict. The debris crisis also represents a unique form of environmental degradation. Unlike terrestrial pollution, which can often be cleaned up given sufficient time and resources, space debris creates a potentially permanent alteration of the space environment. Once the Kessler syndrome begins, it could continue for centuries, effectively closing off entire regions of space to human activities. This would represent an unprecedented loss of natural resources. The orbital regions around Earth are finite and irreplaceable assets that enable satellite communications, Earth observation, and space exploration. Losing access to these regions would be like permanently contaminating all the world's oceans or atmosphere. Future generations might look back on our era as the time when humanity squandered its inheritance in space through short-sightedness and poor environmental stewardship. Just as we now criticize past generations for depleting fisheries, destroying forests, and polluting waterways, future humans might condemn us for making space inaccessible. The psychological and cultural impacts could be equally significant. For the past 60 years, space exploration has served as a source of inspiration and hope for humanity's future. The idea that we could expand beyond Earth has motivated scientific research, technological innovation, and international cooperation. If space becomes inaccessible due to debris, humanity would be forced to abandon its dreams of becoming a multi-planetary species. We would have to accept that Earth is our only home, not by choice, but because we made the alternative impossible through our own negligence. This could have profound effects on human culture and psychology. The frontier spirit that has driven much of human progress throughout history would be fundamentally frustrated. Young people might lose interest in science and engineering if space careers are no longer possible. The loss of space capabilities could also affect our ability to respond to existential threats to Earth. Asteroid impacts, supervolcanic eruptions, and other catastrophic events could potentially be prevented or mitigated using space-based technologies. If debris makes such technologies inaccessible, humanity would be more vulnerable to natural disasters that could threaten our civilization or even our species. On the other hand, successfully addressing the debris crisis could have equally profound positive implications. Developing effective debris mitigation and cleanup technologies would demonstrate humanity's ability to solve complex, long-term environmental problems through international cooperation and technological innovation. Such success could serve as a model for addressing other global challenges like climate change, biodiversity loss, and resource depletion. It would show that humans can learn to manage their impact on complex systems and preserve them for future generations. The technologies developed for debris removal could also have applications beyond space. Autonomous robots, precision navigation systems, and remote manipulation technologies all have potential uses in terrestrial industries. Most importantly, preserving access to space would keep open humanity's long-term options for expansion and development. Even if we don't immediately pursue large-scale space colonization, maintaining the capability to do so preserves options for future generations. Space resources, from asteroid metals to solar energy, represent enormous potential wealth that could support billions of people and enable sustainable development without depleting Earth's resources. Losing access to these resources due to debris would force humanity to find other solutions to population growth and resource scarcity. The next decade will likely be decisive for the future of space activities. The debris population is approaching critical levels, but technologies for mitigation and cleanup are also advancing rapidly. International awareness of the problem is growing, and new forms of cooperation are emerging. Whether we succeed or fail in addressing the debris crisis will depend on our ability to balance short-term economic interests with long-term environmental stewardship. It will require unprecedented levels of international cooperation and sustained commitment to solving a problem whose worst effects might not be felt for decades. The stakes could not be higher. We are making decisions today that will determine whether future generations inherit a thriving space environment full of opportunities for exploration and development, or a contaminated wasteland that serves as a permanent reminder of our short-sightedness. The space debris crisis is ultimately a test of humanity's wisdom and maturity as a technological civilization. Can we learn to manage our impact on the environments we depend on? Can we cooperate effectively to solve problems that transcend national boundaries? Can we think beyond immediate profits and political advantages to consider the needs of future generations? The answers to these questions will be written in the orbital debris that surrounds our planet. Every piece of debris is a vote for short-sightedness over wisdom, immediate gain over long-term sustainability. But every debris mitigation measure, every international agreement, and every cleanup mission is a vote for the opposite. The story of space debris is still being written. How it ends will depend on the choices we make in the years ahead. But one thing is certain: the consequences of those choices will echo through space for centuries to come, shaping the future of humanity among the stars. As we conclude this journey through the terrifying reality of space debris, it's worth reflecting on what this crisis reveals about humanity itself. We are a species capable of incredible achievements. We've built machines that can travel to other worlds, created satellites that connect the globe, and developed technologies that seemed like magic just decades ago. Yet we've also demonstrated a troubling pattern of creating problems faster than we can solve them. The same innovative drive that put the first satellites into orbit also filled that orbit with dangerous debris. The same competitive spirit that drove the space race also led to anti-satellite tests that created thousands of new collision hazards. This pattern isn't unique to space. We've seen it in terrestrial environments where industrial progress created pollution, overexploitation degraded ecosystems, and rapid development outpaced environmental protection. The space debris crisis is, in many ways, the same story playing out in a new arena, but there's reason for hope. Humanity has shown that it can learn from its mistakes and develop solutions to environmental problems, even complex ones. The Montreal Protocol successfully addressed ozone depletion. International cooperation has reduced many forms of pollution. Market mechanisms and technological innovation have made many industrial processes cleaner and more efficient. The space debris crisis presents similar challenges and opportunities. It requires international cooperation, technological innovation, and long-term thinking. But it also offers the potential for new industries, new technologies, and new forms of governance that could benefit humanity in many ways. The companies developing debris removal technologies are also advancing robotics, autonomous navigation, and precision manufacturing. The international agreements being negotiated to address debris are creating new models for global environmental governance. The space traffic management systems being developed could serve as templates for managing other shared resources. Most importantly, the debris crisis is forcing humanity to think more carefully about the long-term consequences of our activities in space. The days of treating space as an infinite dumping ground are ending. Future space missions will need to be designed with environmental considerations from the beginning. This shift in thinking could transform space activities from a source of environmental degradation to a model of sustainable development. Future space missions might actually improve the space environment rather than degrade it. Debris removal systems could be integrated into routine satellite operations. New satellites could be designed to capture and deorbit debris as part of their normal operations. Such a transformation would require fundamental changes in how we think about space activities. Instead of seeing space as a place to exploit resources and discard waste, we would need to see it as an environment to steward and preserve. Instead of prioritizing short-term profits over long-term sustainability, we would need to factor environmental costs into all space activities. The economic models would need to change as well. Currently, the costs of debris creation are externalized. They're borne by the space community as a whole, rather than by the organizations that create the debris. Market mechanisms that internalize these costs, such as debris, impact fees, or cleanup bonds, could provide powerful incentives for more responsible behavior. International governance structures would also need to evolve. The current system of voluntary guidelines and national regulations is proving inadequate for a rapidly growing, commercially driven space industry. More robust international institutions with enforcement capabilities may be necessary to prevent a tragedy of the commons in space. But perhaps the most important change needed is cultural. We need to develop a space environmental ethic that values the preservation of the space environment for future generations. This means thinking beyond immediate national or commercial interests to consider the global, long-term consequences of space activities. Such an ethic is already emerging among many in the space community. Young engineers and entrepreneurs are increasingly motivated by the idea of sustainable space development. Space agencies are incorporating environmental considerations into their planning processes. Commercial companies are beginning to see debris mitigation as a competitive advantage. The space debris crisis, terrifying as it is, may ultimately serve as the catalyst for developing more mature and sustainable approaches to space activities. Just as environmental movements on Earth emerged in response to pollution and resource depletion, a space environmental movement may emerge from the debris crisis. This movement could drive not just technical solutions to the debris problem, but also broader changes in how humanity approaches space exploration and development. Instead of seeing space as a place to escape Earth's environmental problems, we could learn to see it as an extension of Earth's environment that deserves the same care and protection. The children listening to this video tonight will likely live to see the resolution of the space debris crisis, one way or another. They may inherit a space environment that's been cleaned up and protected through international cooperation and technological innovation. Or they may inherit a space environment so degraded that major activities beyond Earth are impossible. Which future becomes reality will depend on the choices made by governments, companies, and individuals in the years ahead. It will depend on whether we can learn to balance our immediate desires with our long-term needs. It will depend on whether we can cooperate effectively to solve problems that affect us all. The space debris crisis is ultimately a mirror that reflects both our greatest achievements and our greatest weaknesses as a species. In the shimmering cloud of metal and plastic that surrounds our planet, we can see both our incredible ability to create and our troubling tendency to destroy. This crisis represents something unprecedented in human history. For the first time, we have created an environmental problem that could literally prevent us from leaving our home planet. Previous environmental disasters, no matter how severe, affected only terrestrial ecosystems. They might have made life more difficult or dangerous, but they didn't threaten to trap humanity on Earth permanently. The space debris crisis is different. It threatens to sever the connection between Earth and the cosmos, cutting us off from the infinite possibilities that lie beyond our atmosphere. In a very real sense, we are at risk of becoming prisoners of our own success, trapped by the very technologies that were meant to liberate us from terrestrial constraints. This irony is profound and deeply troubling. The rockets that carried our hopes to the stars have become chains that could bind us to Earth. The satellites that connected our world have created barriers that could isolate us from the universe. The space age, which began with such promise and optimism, could end with humanity looking up at an inaccessible sky, knowing that we made it so. But perhaps even more troubling is what the debris crisis reveals about our capacity for long-term thinking. For decades, we launched satellites and rockets with little consideration for their long-term fate. We operated under the assumption that space was so vast that our impact would be negligible, an assumption that has proven catastrophically wrong. This pattern of short-term thinking isn't unique to space activities. We see it in climate change, where decades of fossil fuel use have altered Earth's atmosphere. We see it in biodiversity loss, where habitat destruction and pollution have triggered a mass extinction event. We see it in plastic pollution, where convenience products have created persistent contamination of Earth's oceans. The space debris crisis is part of a broader pattern of human behavior where immediate benefits are prioritized over long-term consequences. We excel at solving short-term problems and exploiting immediate opportunities, but we struggle to manage the cumulative effects of our activities over decades or centuries. This pattern raises profound questions about our fitness as a technological civilization. Can a species that evolved to focus on immediate survival threats successfully manage technologies with long-term, global consequences? Can we learn to think beyond our individual lifespans and immediate interests to consider the needs of future generations? The space debris crisis offers a test case for our ability to address these fundamental challenges. Unlike climate change, which involves complex interactions between human activities and natural systems, space debris is a purely human-created problem. There are no natural processes that contribute to orbital debris, and no uncertainty about the cause and effect relationships involved. This clarity makes space debris both easier to understand and harder to excuse. We can't blame natural variations or scientific uncertainty for the debris crisis. It is entirely the result of human choices and human technologies. If we can't solve this problem, it raises serious questions about our ability to manage other technological challenges. The debris crisis also tests our capacity for international cooperation. Space is a global commons that affects all nations and all peoples. No single country can solve the debris problem alone, and no country can isolate itself from the consequences of debris created by others. This creates an imperative for unprecedented levels of international cooperation and coordination. Countries must share sensitive information about their space activities, coordinate their orbital operations, and potentially subordinate some national interests to collective safety. These requirements challenge traditional notions of sovereignty and national autonomy. The commercial space industry adds another layer of complexity. Private companies operating for profit may have different priorities and incentives than government space agencies operating for national prestige or scientific advancement. Aligning commercial interests with long-term environmental stewardship requires new forms of regulation and market mechanisms. The generational implications of the debris crisis are particularly sobering. The children and young adults alive today will live with the consequences of decisions made about space debris over the next decade. If we fail to address the problem, they may inherit a world where space exploration and satellite communications are relics of the past. This intergenerational aspect gives the debris crisis moral urgency that transcends immediate economic or political considerations. We are not just deciding about the future of space activities. We are deciding what kind of world to leave for our children and grandchildren. The psychological implications are equally significant. For 60 years, space exploration has served as a source of inspiration and hope for humanity's future. The idea that we could expand beyond Earth, explore other worlds, and eventually become a multi-planetary species has motivated scientific research, technological innovation, and international cooperation. If space becomes inaccessible due to debris, humanity would lose this vision of an expanding future. We would be forced to accept that Earth is our only home, not by choice, but because we made alternatives impossible through our own negligence. This psychological shift could profoundly affect human culture and motivation. The loss of space capabilities could also affect our resilience as a species. Earth faces numerous natural threats, from asteroid impacts to supervolcanic eruptions, that could potentially threaten human civilization or even human survival. Space-based technologies could provide early warning of these threats, or even methods for preventing or mitigating them. If debris makes space technologies inaccessible, humanity would be more vulnerable to natural catastrophes. We would lose both the early warning capabilities that space-based sensors provide and the potential for space-based intervention technologies The debris crisis, therefore, represents more than just a technical or economic problem. It is a test of our wisdom as a technological civilization. Can we learn to manage the long-term consequences of our activities? Can we cooperate effectively to solve problems that transcend national boundaries? Can we balance immediate interests with the needs of future generations? These questions will be answered not by philosophers or politicians, but by engineers, entrepreneurs, and international negotiators working to address the debris crisis over the next decade. Their success or failure will determine not just the future of space activities, but the trajectory of human civilization itself. The stakes could not be higher. We are deciding whether future generations will look back on our era as the time when humanity learned to be responsible stewards of the space environment, or as the time when we squandered our cosmic inheritance through short-sightedness and greed. In the end, every piece of space debris is a vote for one future or the other. Every satellite launched without proper disposal planning. Every collision that could have been avoided. Every international disagreement that prevents cooperation moves us closer to a future where space is inaccessible. But every debris mitigation measure, every successful international agreement, every innovative cleanup technology moves us toward a different future, a future where space remains open for exploration, development, and the expansion of human civilization. The choice is still ours to make, but the window for action is closing as rapidly as debris orbits the Earth. At 17,500 miles per hour, that window won't stay open much longer. But mirrors also offer the opportunity for self-reflection and change. As we look up at the invisible debris screaming overhead at 17,000 miles per hour, we can choose to see it not just as a threat, but as a teacher. It can teach us about the consequences of short-term thinking. It can teach us about the importance of international cooperation, and it can teach us about our responsibility to preserve the environments that support our civilization. The terrifying truth about space debris is that it represents humanity at a crossroads. We can continue down the path of environmental degradation and resource exploitation, ultimately making space inaccessible to future generations. Or we can choose a different path, one that leads to sustainable space development and the preservation of opportunities for human expansion among the stars. The choice is ours. The consequences will echo through space for centuries to come. And right now, as you listen to these words, those consequences are being written in the trajectories of 34,000 pieces of trackable debris and millions more too small to see, all screaming through the darkness at speeds that turn paint chips into bullets and dreams into nightmares. But they don't have to remain nightmares. With wisdom, cooperation, and determination, we can still choose a different ending to this story. We can still choose to be the generation that learned to live sustainably in space, rather than the generation that squandered humanity's greatest frontier. The debris is still up there, still dangerous, still growing, but it's not too late. Not yet. The question is whether we'll act quickly enough, cooperatively enough, and wisely enough to preserve the infinite possibilities that await us among the stars. Because in the end, space debris isn't just about space. It's about who we are as a species and who we choose to become. And that choice, like the debris itself, is still traveling through the darkness, waiting to see where it will land.